Hello everyone. So today I'll move with my third lesson. I hope previous lectures were clear to you all. So today in lesson number 3 we will talk about intrinsic and extrinsic semiconductor. I have two videos on the same topic. So this lecture will be the first part of intrinsic and extrinsic semiconductor and the second will be lesson number 3. So let's start. Before entering into an extrinsic and intrinsic semiconductor, let's see some electrical properties of germanium and silicon. I'm not asking you to remember the same points for every element, but at least if you are preparing for any examinations, you have some little bit idea about these two elements like germanium and silicon. So at least remember these things or get some idea. So for germanium your atomic number is 32 and for silicon it's 14. Density of atom is like 4.421 into 10 to power 22 and for silicon it's 5 into 10 to power 22 and intrinsic concentration at 300 Kelvin it's 2.5 into 10 to power 13 for germanium and for silicon it's 1.5 into 10 to power 10. Intrinsic resistivity at 300 Kelvin it's 45 and for silicon it's quite huge value. I'm like assuming that you know the resistivity unit. Obviously it's ohm, meter or centimeter, anything. Leakage current it's like nanoampere for silicon and microampere for germanium and the operating temperature is 75 degrees Celsius for germanium and for silicon it's 175 degrees Celsius. So at least remember these values for your sake. Okay, now why generally silicon is preferred than germanium? There are certain reasons for this. Silicon is always having a smaller leakage current which is preferable, so we prefer silicon than germanium. It is having high power handling capacity, it is having high temperature applications, and if you remember, if you have gone through my previous lessons, I have discussed the reason for every point, so go through my previous lectures to be very clear on the statements. Silicon is plenty available on the surface of earth and this is a very primary reason why silicon is very much fancy these days. Silicon is very economical and cheaper, so we prefer silicon, and the silicon has the good favorable property to form silicon dioxide, and this last point is the main reason why silicon is very much fancy by integrated circuit manufacturers. Now we have certain points that makes you to think that silicon is preferred than germanium, but there are still some disadvantages for silicon. Okay, let's see the disadvantage for silicon. Silicon is a semiconductor material and when it is exposed to a high temperature, you can say 1400 degrees Celsius temperature, it will melt and will give you liquid form silicon, and when that liquid react with oxygen it will give you silicon dioxide. You can see in the block I have mentioned that silicon at the very high temperature is mixing with oxygen and it's giving you silicon dioxide. Silicon dioxide is a perfect insulator and it is used to provide insulation. It's providing you the isolation in between the components during IC fabrication. So silicon dioxide provides you the isolation. Okay, the one question you can raise here is IC fabrication in silicon dioxide is for providing what? It's just for providing insulation. So in exams they directly ask you this question, so remember that it's for providing insulation. Okay, let's start with intrinsic semiconductor. Intrinsic semiconductor is also called as non-degenerate semiconductor. Why it's non-degenerate semiconductor? Why we call it? Intrinsic means pure. We don't have any impurities in intrinsic semiconductor. It's a pure form. So that's why it's a non-degenerate semiconductor. Okay, so let's see one by one about, and we will enter into the depth of intrinsic semiconductor. So first is your crystalline structure at 0 Kelvin. Here this is a crystalline structure. I have used the same elements throughout the structure, which is having 4 valence electrons throughout, and the other side I have the energy band diagram of the same crystalline structure at 0 Kelvin. Okay, so the sharing of electron with neighboring atoms is called covalent bonding. This blue dotted line forms the covalent bonding, and this red are the electrons which help you to complete the bonding, and the structure goes on. I have just taken a block of it and tried to explain this. In one covalent bonding there will be 2 valence electron. If it's gaining 2 valence electron, it's completing its bonding. Okay, at 0 Kelvin all the valence electrons are in perfect covalent bonding. Second point is intrinsic semiconductor at 0 Kelvin will be working just like as an insulator. You remember insulator doesn't have any conductivity because they don't have any electrons or holes in the flow to provide any conductivity, so they don't have any conductivity. This also I have like mentioned in my previous lectures, they don't have any conductivity. Okay, whatever points I have discussed, every point I have mentioned here in the statements. Sharing of electrons with neighboring atom is called covalent bonding. In one covalent bond there will be 2 valence electrons, and at 0 Kelvin all the valence electrons are in perfect covalent bonding, so 0 Kelvin will be working as an insulator. At 0 Kelvin it will be working just as an insulator. So now what happens when you increase the temperature? At 0 Kelvin there is no conductivity, so it's working like an insulator. So what happens when we increase the temperature? Okay, I have mentioned the crystalline structure on the right hand side and the energy band diagram on the other side. So when you raise the temperature, covalent bond is broken and it will create 1 electron and 1 hole. This in this structure you can see with orange color, I have mentioned that it's a hole and the other is the free electron. Because when bond is broken, you can see here the dotted line, it's just on the one side, other side I didn't mention. In the entire structure you can see that I have taken 3 covalent bonds which are broken. This is 1, this is 2 and this is 3. Okay, and every time when the bond is broken, it is generating an electron and a hole. Electron is moving into some free space and your hole will be residing in the covalent bonding. Okay, so when covalent bond is broken, it will generate 1 electron and 1 hole. The electron will be jumping from valence band to conduction band and become a free electron, while the hole will remain in the valence band. What is hole? Hole is basically defined as a deficiency of an electron in the broken covalent bond. Hole is also the carrier of current. As electron is your carrier of current, hole is also the carrier of current, but the only difference between the electron and the hole is a positive charge of 1.6 into 10 to power minus 19 coulomb, and your electron is having the same value with the negative. Okay, in intrinsic semiconductor n is equal to p. Now why it's n is equal to p? Because we have same number of electrons and same number of holes. Whenever the bond is broken, it's generating equal number of electron and holes. We don't have any kind of doping, we don't have any kind of impurity, so every time n is equal to p, so we have intrinsic semiconductor n is equal to p, and we have assumed that n is equal to p is equal to your intrinsic concentration. That's indicated with this notation. Next, let's see the intrinsic conductivity. You remember this formula I have mentioned in my previous lecture. In this, the conductivity formula is the same, but for intrinsic semiconductor, N is equal to P because the holes and the electrons are same. So just remember, for intrinsic, as N is equal to P, you're just replacing the values. I mean, I'm taking N is equal to P, so, and that is equal to intrinsic concentration, that is N base I. So I've taken this thing common and taken this thing in bracket. Now further, you should know that the conductivity is directly proportional to intrinsic concentration, and intrinsic concentration is directly proportional to T to the power 3 by 2. That makes a statement that whenever you are increasing the intrinsic concentration, the temperature, whenever you're increasing the temperature, your intrinsic concentration will increase as a non-linear variation. Okay, that means in intrinsic semiconductor, your conductivity will increase with temperature. Whenever you are increasing the temperature from 0 to 300 Kelvin, your conductivity is increasing. Okay, so in intrinsic semiconductor, conductivity increase with temperature. Fourth is intrinsic resistivity. This is the notation. Resistivity is just equal to 1 by conductivity. I have just taken the same formula and put over here, so you can see the formula. Okay, the next is generation of electron hole pairs. Some points I didn't mention so deeply because it's not needed. You just get to know that what is the generation of electron hole pairs and all. What is generation of electron hole pairs? The process when electrons and holes are generated in pairs due to the breaking of covalent bond is known as generation of electron hole pairs. Okay, recombination. Sixth is your recombination. Now what's this recombination? Recombination is basically a free electron pairing with a hole. That means during recombination, free electron and hole both will disappear and the covalent bond is created. The same thing I have mentioned here. During recombination, the free electron will be falling from covalent band to valence band to recombine with a hole, and a difference of energy is dissipated in the form of heat and light. Recombination is basically, in simple words, it's just a reverse procedure. Everything is going backwards and recombining and again forming its bond. So just get an idea that recombination is just a reverse procedure. Seventh is Carrier lifetime, notated with tau. It's an interval of time from breaking of covalent bond until its recombination. The entire time which is take from breaking of the covalent band and again it's coming for recombination, the whole time is known as Carrier lifetime. This Carrier lifetime, remember, it's also known as average lifetime, and the range is from microseconds to milliseconds. Disadvantage for intrinsic semiconductor. What is the disadvantage of intrinsic semiconductor? It has only one drawback, that its conductivity is very small. They cannot raise their conductivity. Okay, and one note you should remember, that the only semiconductor device fabricated with intrinsic semiconductor is your pin diode. Generally asked in examinations, so remember pin diode. We'll discuss the pin diode in our semiconductor lecture, so wait till that. For the time being, remember this statement. Moving to next, let's understand what is doping. Doping is mainly adding impurities to a semiconductor is doping. Doping always increase your carrier concentration. So why we require doping? As you know that in previous intrinsic, the conductivity is very less. So we will dope with some doping to increase the carrier concentration. Okay, So we have three kind of standard doping levels, and you should strictly remember these three dopings. In examination they directly ask you three kind of dopings or the values, so be very clear with these three kind of dopings. First is your moderate doping. I have given the range, that's 1 is to 10 to power 6 to 10 to power 8. Lightly doping is 1 is to 10 to power 11. Highly, or you can say heavily doping, is 1 is to 10 to power 3. Remember that minimum doping required to convert intrinsic semiconductor to extrinsic semiconductor is 1 is to 10 to power 8. It's a minimum requirement, otherwise the intrinsic won't be getting converted into your extrinsic semiconductor. It will remain intrinsic semiconductor. When intrinsic semiconductor is slightly doped or it's not reaching the minimum criteria, then it will again remain intrinsic. It won't be getting converted into extrinsic semiconductor. Okay, so from these three standard doping, they can raise a question, moderate doping refers to. So if you remember these three, you can directly mark up your answer. And remember that I have mentioned 10 to power 6 to 10 to power 8. So remember, if they ask for moderate doping, just tick the 10 to power 6, not 10 to power 8. So that's why I basically put this question over here, that mark A option, not D option. Okay, moving to next. Now, what kind of dopings you can use? There are two impurities that you can add into the crystalline structure. Is your first trivalent, also known as acceptor impurities, or pentavalent or donor impurities. These are certain examples. They are having trivalent electrons and this having pentavalent. Trivalent is +3 and pentavalent is 5. 5 means 5 valence electron and trivalent means 3 valence electron. Now why it's acceptor? Acceptor means because it is having 3 electrons, it will try to grab one electron to complete its bonding. So it will try to accept the electrons. So it's acceptor. Pentavalent, it's already having the 4 electron to complete the bonding with the neighbor elements, and it have one extra electron that they can donate to some other to complete the bonding. So that's why it's donor impurities. Question we can raise here is one question: conductivity increased by how much with 1 is to 10 to power 8 doping in germanium? This question I have seen in many exams, so I've just put over here that you should know that it increases by 12 times. Just remember this. Now, extrinsic semiconductor, also known as degenerate semiconductor or dope semiconductor. I hope that it's clear to you that why it's called dope semiconductor. As intrinsic semiconductor was not having that much conductivity, and that was the drawback. We need to overcome with that drawback, so we are doping the intrinsic with some doping and it will form the extrinsic semiconductor. Okay, in extrinsic we have two kinds of semiconductor now. The first is your N-type semiconductor, which will be the donor one, and the P-type semiconductor, also known as the acceptors one. Okay, let's see one by one. For N-type semiconductor or donor, here the impurity will be the pentavalent. Pentavalent will be 5 valence electrons. Let's see the crystalline structure at 0 Kelvin. Here is the crystalline structure. You can see the same structure I have repeated. The only difference is at the center I have kept the impurity, that is pentavalent, that is +5. +5 with the black I have mentioned the electrons, 5 valence electrons of this impurity. With the 4 electrons, they are engaged in the bonding, but the 5th electron is free electron. Okay, I have mentioned with this red colored 5th electron, and this is the energy band diagram. Okay, so this 5th electron is also known as excess electron, which is unable to participate in the bonding. This free electron is having a force of attraction to the parent atom. or you can say the impurity atom. Though this is the energy band diagram, you can see the covalent band here, it's empty, valence band it's totally filled, and with this dotted line with this blue color, this is your donor energy level indicated with notation E base D. Okay, donor energy level is a discrete energy level that is created just below the conduction band, as you can see in the figure. Your donor energy level represents the energy level of all the pentavalent atoms added into the semiconductor, your semiconductor device. Okay, at 0 Kelvin, the fifth electron will be existing in the donor energy level. I mean, whatever you are having the fifth electron, don't worry whether you have 3 or 4 fifth electron, all the fifth electron will be existing in this donor energy level in this blue line. As I have given you this example, this one, just we are talking about one in this figure, so this is stuck in your donor energy level. The fifth electron is not in the covalent bonding, as you know, and it is not also the free electron, but it is a bonded electron to parent atom. It's always bonded towards a parent. That's why it's somewhere near to the parent atom. Okay, at 0 Kelvin, the fifth electron of all the impurity atoms exists in this donor energy level, as you can see here. Every fifth electron will be residing in this same discrete energy level. Now what is this for germanium and silicon? I have mentioned here. What is this? This is the additional energy which we require to detach the fifth electron from your orbit. For germanium it's always 0.01 electron volt, and for silicon is 0.05 electron volt. Try to remember these values. They directly ask you the questions, like as let you know. Here whatever points I have mentioned, every point I have told you, that donor energy level is a discrete energy level created just below the conduction band. Free electron is having a force of attraction to parent atom. At 0 Kelvin, the fifth electron will be existing in the donor energy level, and every point I have discussed. At 0 Kelvin, the fifth electron of all the impurity atom exists in the donor energy level. Okay, so one question which comes in the exam directly is, they just ask you how much additional energy is required to detach that bonded electron. So the value is different for both germanium and silicon. For germanium is 0.01 and for silicon it's 0.05. Okay, now what happens when you raise the temperature to 300 Kelvin? Again you see the crystalline structure is same thing, everything. As you know, when we raise the temperature, there's a breakage of covalent bonding. So I've shown you the broken covalent bond, and they generate the hole and the electron. Okay, you can see here with the orange color. So, and this is the energy band diagram. This is a covalent band, upper side lowers the valence band, and donor energy level is represented with the dotted blue line. And this is the impure fifth electron, that reside in your donor energy level. So what happens at 300 Kelvin? As temperature increases from 0 to 300 Kelvin, the fifth electron will be moving from donor energy level into the conduction band. As you can see here, I have shown with the arrow that's moving towards the covalent band, and it's the process is because of donor level ionization. Now what is donor level ionization? Donor level ionization refers to the fifth electron moving from donor energy level to the conduction band. This is a procedure that how the electron is moving from your level to the conduction band. This is known as donor level ionization. Donor level ionization increase with the increase in temperature. It doesn't remain constant. It will increase as you increase the temperature. At one point, the whole electrons will be moving towards the covalence band. Okay, so You can see this procedure is known as donor level ionization. So I was telling you, when you increase the temperature, there will be a donor level ionization process, and because of thermal energy, a number of covalent bonds will be broken and equal number of electrons and holes are generated, and there will be an electrons which will be moving from valence band to covalent band, and they will become the free electrons. As you can see here that we have more number of free electrons rather than holes, because we already have one free electron. When you're breaking the covalent band, there will be more free electrons, right? So you can see the electrons are more in number than holes. The concentration of free electrons in the conduction band is far greater than concentration of holes in valence band. So we can say that electrons are the majority carriers and holes are obviously the minority carriers. Okay, so each and everything whatever I have discussed, I have mentioned the statement, you can go through. Now, why it's N greater than P? Why it's very much greater than P in N-type semiconductor? So just to make it clear, I have mentioned this in the question answer form. The concentration of free electron in the covalent band is far greater than the concentration of hole in valence band. I've already shown you this in the figure. So electrons are very clearly the majority and the holes are the minority. Okay. There are two statements like majority carriers will contribute more current with less noise, and minority carriers will contribute less current with less noise. Why is it so? How you can say that? Okay, since minority are smaller in number, they are less in number, as you increase the temperature, they start vibrating, and due to this thermal vibrations, they produce more noise. Minority carrier noise is also known as thermal noise, and it increases with temperature. Whenever you increase the temperature, they increase with that same value. In N-type semiconductor, current is always predominantly dominated by the flow of electrons. When you have more number of electrons, it's always N-type semiconductor. So conductivity is due to the minority carrier is almost negligible. You can see in this block I'm trying to explain you that majority are the electrons that are almost greater than 99.99%, and minority is almost negligible, that's 0.01%, and this 99.99 is a huge percentage. So you can say that electrons are huge in number. So the condition for N-type semiconductor is N is greater than intrinsic concentration and P is very less than intrinsic concentration. Why is it so? Because in N-type semiconductor, as electron concentration is increasing above intrinsic concentration, the whole concentration will be falling below the intrinsic concentration, and this is because of recombinations. This thing I can say just because of recombinations. Okay, the third is law of electrical neutrality. Law of electrical neutrality states that your ND, that is density of donor atoms, plus holes, that P, is equal to density of acceptor atoms plus electrons. Here when we are talking about N-type semiconductor, means Na is 0. Na is 0 because we are not talking about acceptors, we are just talking about donors. So there will be an existence of donors, that is N base D only. So when you're when you're placing your Na is equal to 0, you will just directly get this thing. So we're just assuming that holes are almost negligible, so we are just neglecting this P and we are making N almost equal to your density of donor atoms. Fourth is conductivity of N-type semiconductor. Okay, this formula you're very much aware. You're just putting the same above thing into this thing. Your P is negligible, so you're removing this P thing, and in the place of small electrons N, you are putting density of donor atoms. Okay, Okay, moving to the B, that is P-type semiconductor, acceptor, or say positive type semiconductor. If you heard my N-type semiconductor explanation, it will be very easy for you to go through P-type semiconductor, and it's almost same. The difference I'll let you know one by one. Here, there we were having the impurity as pentavalent, but here it will be the trivalent. It is accepted because it will try to accept the electrons to complete its bonding, and when something accepts, they gain positive charge, so it's a positive type semiconductor. Okay, crystalline structure at 0 Kelvin. What happens at 0 Kelvin? Here I have shown you the crystalline structure. You can see that same structure is here, but at the center, instead of pentavalent, we are using trivalent impurity. You can see they have 3 valence electron and all are busy in their bondings, but the fourth, it doesn't have any free electron to complete the bonding, so it's incomplete bond. And this is the energy band diagram, same thing, same everything. The only difference is there we were having donor energy level, here we'll be having accepted energy level, and it will be close to valence band instead of covalent band. There it was very close to covalent band, but here it will be very close to valence band. Okay, and same, your additional energy which will be required to detach will be the same for germanium and same for silicon. Okay, now this red dotted line, which is your discrete energy level, is created just above your valence band, and it's denote the energy level of all the trivalent atoms added to your semiconductor. Remember, I've discussed about pentavalent, but here it will grab all the trivalent atoms which will be adding to the semiconductor. So same statement I have discussed in this statement, same lines, right? So every impurity atom will be receiving 1 electron to complete its bonding. So P-type is also called as acceptor. I've already told you why it's acceptor, because it's accepting something. And again, P-type semiconductor 0 Kelvin will be working as an insulator because it doesn't have any conductivity at 0 Kelvin. Okay, so what happens when you raise the temperature at 300 Kelvin? At 300 Kelvin, because of thermal energy, large number of covalent bonds will be broken and equal number of electrons and holes are created. Let's see with the figure. Here's the figure. It's the same crystalline structure. At high temperature, bonds are broken. You can see the one side we just have the dotted line. As soon as it's getting broken, they will be generating one hole with this orange color, and the other electron, which was free electron, this incomplete bond, just grab that electron to complete the bonding. You can see I have just indicated with this orange dotted line that it's grabbing, and I mentioned that it's complete its bonding. So you can at least have an idea that what happens at 300 Kelvin. This is the energy band diagram, so let's understand this. I'll let you know that when P-type semiconductor is room temperature, it's a room temperature or 300 Kelvin, because of thermal energy, a number of covalent bonds will be broken, and again equal number of electrons and holes will be created, as you know very well. Most of these electrons will be moving from valence band into the energy level. This is the accepted energy level which I'm talking about. Most of the electron will be moving from here to here, and the very few electrons will be moving to covalent bond. This won't be allowed to go to the covalent bond. They'll be stuck in this level. So we can say that your electrons will be very less in number as compared to holes. So there will be very few electrons will be moving from valence to conduction band. Therefore you can say the holes are majority, as I have already shown you in the figure that holes are 3 in number but electrons are only 2. Just I'm trying to give you the idea that electrons and holes have different concentration. Okay, hole concentration and valence band is greater than electron concentration. I have shown you in the figure. And same thing here, there we were having the electron as majority carrier, but here we will be having a hole as majority carrier and minority as electrons, and conductivity will be mainly due to the holes, that is 99.99%, and electron will be contributing almost less than 0.01%. Similarly, condition for N-type semiconductor, condition for your P-type semiconductor will be like okay, just a second. I have just one mistake I think I have done is condition for N-type semiconductor. When we are talking about condition for N-type semiconductor, I have just a second. Okay, here instead of N we're talking about P, so I'm sorry, I've just P. We're talking about P-type semiconductor, so P will be holes. So very sorry for the disturbance. So okay, so condition for your P-type semiconductor, sorry for the disturbance. Let's move to the same slide. Okay, so I was telling you that condition for N-type semiconductor was N was greater than intrinsic, but here will be the holes greater than intrinsic concentration and your electrons will be less in number. Therefore, holes will be the majority carriers and your electrons will be the minority carriers. Okay, so again the law of electrical neutrality, same, everything is same, you're just replacing with ND, that is density of donor atoms. So you can see here that here we don't have acceptor atoms, sorry, here we don't have donor atoms, here we're just talking about acceptors. So your donor will be 0 and you're just putting Na, so you're getting the P almost equal to your density of acceptor atoms. You're ignoring the electrons. Conductivity for P-type semiconductor is very much similar to N-type. You are just replacing with Nd with Na. Okay, and the two questions which I found to discuss with you, and it's quite important that in examination they directly put the question that N-type semiconductor is what? They give you 4 options, so remember that it's electrically neutral. If they don't give you an option, just remember the other way, that's always electrically neutral. I am not discussing this topic in detail because it's a conventional question, and just want you to know that whenever you go through this electrical neutral derivation in your EDC subject, go through it very properly. And because in IES sometimes IES examinations they just put the conventional question of 4 to 6 marks, so whenever you go through your EDC subject, get proper thorough knowledge about this derivation. Okay, so here I am like getting over with this lesson number 3. Thanks for watching, and I hope you got all the points and it was clear to you. So please do like my video and give a thumbs up and stay in touch. Thank you so much.